Fantastic. Yeah. All right.
Yeah.
So yeah. So thank you for volunteering, and hopefully, we can sort of track whether things are making sense. Right. So I'm going to quickly recall what we started last time. So we were looking at basis and dimensions. So we looked at the notion of. So we wanted to define a notion of basis, and for this we started by defining. The notion of linear dependence, right? So we said that distinct vectors, alpha 1 to alpha n, um, uh, suppose that you have these vectors in S, right? And you have some scalars in the field. Then if there exist such scalars that allow you to combine these vectors weighted by the scalars to give you a 0, then we would say that these vectors are linearly dependent. That was the definition. And a set of vectors that is not linearly dependent, so there doesn't exist any C's except all zeros, such that this can be satisfied, those would be called linearly independent, right? So this is sort of straightforward. Oh, Tarsh, you can keep yourself unmuted. It's fine. That way, I can get a quick feedback. I don't have to look up every time, if that's
Uh,
okay with
no, so I have some noise in my background, so I
you.
don't
It's okay.
hear
We
you.
don't hear
Yeah.
the noise. We
Yeah.
don't hear the noise. It's fine. Yeah.
Them.
The voice cancellation is good. If there is noise, I'll tell you. Okay, don't worry about
Yeah.
it. Is that okay? Okay.
Yes,
Okay.
sir.
Perfect. So the definition is fine, right? The definition of linear dependence and linear independence. Uh, Darsh?
Yes, sir. Yes, sir. It is.
Okay. Okay. Perfect. Yeah. Sorry, I didn't catch that. All right. And if the set contains only finitely many vectors, if the set contains only finitely many vectors, then instead of talking about the set, we can talk about the vectors directly. So we'll just refer to these vectors as a sequence and say whether or not these vectors are dependent or independent. Okay, so that's just a small distinction. And here are some easy consequences of this definition. So the first consequence is that any set that contains a linearly dependent set is linearly dependent. So suppose there is some set S prime, right? Today it's causing a little bit of, so suppose there's some set S prime, right? And we have S union some elements, I don't know, V1, V2, and so on, Vk. And we know that this thing is linearly dependent. Then S prime is linearly dependent. Right? Tarsh, do you see why this is?
Yes. Yes, sir. Yes.
Okay. Why is it the case?
Yes.
Why is S prime linearly dependent?
It will be linear. No, it is kind of trivial, right? So, uh, is a zero. Okay, I'm unable to explain it properly, but uh,
Mm-hmm.
uh, yeah.
Right. No. So okay. So the
So,
idea here is, what is the definition of linear dependence? Right. The definition of linear dependence says that uh, there should exist some distinct vectors, right? So you should have some sequence of vectors from the set, such that when you take a linear combination of these, it gives you 0 with some scalars, right? So I'm already telling you that you have a set S which is linearly dependent. So this implies that there exists some vectors, right? Alpha 1 to alpha n, such that, and some scalars C1 to Cn, right? Such that Ci alpha I is 0, correct?
yes, sir.
Okay. And now to show that S prime is linearly independent, we also need to show the same, right? We want to show that there exists alpha 1 prime all the way to alpha n prime, right? Let's call it alpha m, doesn't matter, that are in S prime, such, and some C's exist, right? And C1 prime to Cn prime, such that sum over I, C prime I alpha I prime, correct? So can you tell me what so what should alpha I prime and ci prime be, given what I've told you? Yeah, does anybody else want to answer? If Darsh is, does somebody want to help Darsh? Maybe feel free to speak up. Okay, you don't have to. Nobody at all.
Hello, sir.
Hi. Yes. Tell me.
Can you hear me?
Yes. I can hear you. Tell me.
I didn't entirely understand what exactly linearly dependent means. Do you explain it again?
Linear dependence is right here. Right. We are saying that a subset S of some vector space V is said to be linearly dependent if there exist distinct vectors alpha 1 to alpha n in the set S, right? So S is some subset of V, right? We say S is linearly dependent if there exist
Okay, so
distinct
it's a
vectors. So alpha 1 not
non-trivial.
equal to and
So
C1.
non-trivial. What's the difference between this and non-trivial?
Where is non-trivial written?
No, I'm just thinking if it seems like the opposite of trivial.
Yeah. So here we are saying that the C's are not all zeros. So they are linearly dependent if you can
But is
find a
this
linear
linearly dependent just trivial?
Sorry,
Independent,
what?
is it trivial?
What is trivial? What do you mean by trivial? What do you have in mind when you say
So
trivial?
a1x plus all of that combines to 0, which makes x equal to 0, which allows A to be any solution space, correct? Is that trivial?
Yeah, we are not talking about yeah, so that was when we were discussing linear equations, right? So then at
Yeah,
that point
vectors
these were
and linear.
matrices. Yeah, and x were at that point we were treating x as uh, yeah, basically solutions, right? We hadn't really discussed vectors. Now we're talking about vectors.
Yeah, but
So
aren't
indeed, that is
vectors
one
and
special example. That is correct. It is a special example, what you're suggesting. But the okay, so by your definition, so if you want to extend that idea that we had in the previous section, trivial would basically correspond to having CIs, all CI are zero. Okay, so this is what trivial would mean in this context. That the only way you can show that this sum of vectors is zero is if all C's are zero. So the only solution, if you like, to alpha sum over I ci alpha I equal to 0 is ci equal to 0 for all I. Okay, this is what trivial would mean here. But we don't have to
okay.
unnecessarily talk about trivial here because that was introduced in a different context, right? We were talking about solutions of linear equations and we were saying that the only way you can solve the linear equation is if all the x's are zero. That is not what we are doing here. Here, it is related, of course, because we are generalizing the properties. But here we're just defining linear dependence. And you are right
So,
in your intuition that
yeah, I posed the formal definition. Would it mean that trivial belongs to linearly independent? It's a subset of linearly independent.
so trivial is not a formally defined term, right? We are not defining trivial here. Trivial normally would just mean that the only way you can solve a system of equations is if all x's were zero. And if you want to think of it that way, you can think that you're asking what is the set of c's that
So
would
it's
solve
possible,
some.
but it's redundant.
Yeah, so we are
Or,
not mixing the terminology here. You could generalize the notion of trivial, but we are not quite doing that here.
okay,
It would probably add some confusion, yeah. But for now, we're just trying to say that something is linearly dependent if you can combine the vectors with some weights such that the sum is a zero vector, which is what is written here. Is that okay?
yes, my doubt is clarified. Thank you.
Okay, perfect. Okay, so does somebody want to answer this question here? So what should alpha
Sir,
prime
am
and
I
C
audible?
prime be? Yes. Can you identify yourself?
Yes, I am Tej.
Page. Okay, yeah. So do you want to answer the question?
Yes, yes, sir. First, I'd like to ask about like, is it necessary for all of the vectors in the space to be used, or can we just use some of the vectors to say that C1 alpha 1 plus and so on will be 0?
Sorry, just give me a second. I'm Shantanu. I'm getting a call and it may be important. Just give me 1 second. I'm very sorry for this.
Yeah.
Just one moment, please. I am teaching. I'm teaching. Yes. Okay. Bye. Yeah. Okay. Sorry. Yeah. Um. Yeah, that was my friend. I thought that there was an emergency. He called like twice or thrice, so I got a bit concerned. Sorry. Okay. Great. Sorry. What were you saying, Tej? Can you hear me, or did the audio get messed
So,
up?
yeah. So, it's not necessary to use all of the vectors in the set for this condition,
Exactly.
right?
Exactly. Very good thinking. Okay.
Yes, so we can just ignore all of the vectors that are not in the linearly dependent set and just
Exactly.
use the ones in the linearly dependent set to create 0.
Exactly. So in terms of what I've written to capture your idea, so these alphas, right? These alphas were the vectors in the initial set, right? They were in S, and I can take alpha I prime just to be alpha I, exactly the vectors I had taken earlier, right? Which were linearly dependent, and I can take the Ci primes to be Ci, right?
Yes,
Does it make sense? So I'm just
yes,
formally writing down what you said. Okay, it's exactly what you're saying. Very good. Okay. Any more questions? Are things making sense?
yes.
Okay, perfect. Tej, do you mind staying? Oh wait, somebody said something on the chat. Yeah, please don't put things on the chat, okay? Because it's a little bit harder for me to follow. Just speak up because there's already not too much crosstalk, so it should be fine. Okay, so Tej, so let's continue, right? Then any subset of a linearly independent set is linearly independent. Is this one clear?
Yeah,
Right. So the idea is very similar, right? Because okay, the idea is very similar, right? Because if you have if there's like a bigger set, right, and from this already you cannot make independent vectors. Of course, if you take a smaller set, you will not be able to make independent vectors, right?
yes,
Okay, and then in any set which contains the zero vector is linearly dependent. Okay, so how do we see that? Because, so remember, what is the condition for linear dependence? That you have to find some non-zero C's. You have to find some sequence of vectors and some non-zero C's such that when you sum them, you get 0. Okay, so if you have a 0 vector in the set, right, we know that any C times the 0 vector gives you a 0 vector, right?
yes,
Okay, so that immediately tells you what? It tells you that, sorry, so it tells you that you have satisfied the definition of being linearly dependent, right? Because you found a non-zero C and a vector in the set such that you get 0, correct?
yes,
Okay, perfect. All right. And then a set S of vectors is linearly independent if and only if each finite subset of S is linearly dependent. Okay, so what is this saying? It is saying that you take a set S of vectors that is linearly independent. Okay. Then this would imply that, I don't know what's happening to the pen today. It's ridiculous. So this would imply that, just give me a second. Let me close this and start again. I don't know why it's causing trouble today. Why can't I close the... What is happening? Okay. Give me a second. Then I don't know. I'm not able to write down properly on the tablet. Just give me a second. Okay, hopefully it will have fixed itself now. Okay, I know it's good. All right. So what are we saying? We're saying that a set S of vectors is linearly independent this would imply, so it's both sides, right? If and only if means that the implication holds in both directions. So it would imply in particular that each finite subset of S is linearly independent, right? So a finite subset of S, so this already follows from point 3, right? Wait, who was I talking to? I forgot.
Yeah.
Tej, was it? Yeah, Tej.
Yes.
Tej, right. So this is clear, right? So if property 3 was, what was property 3 saying?
Sir, I believe it should be from property 2, right? The forward proof.
Oh, yes, exactly. Sorry, yeah, property 2. Very good. So what does property 2 say? Yeah, okay, of course you understand. That's why you said, okay, good. Right, so property 2 is saying that a subset of linearly independent set is also going to be linearly independent, which is what this guy is saying, that you take any finite subset, you will get a linearly independent set. So this direction is fine. And for the other direction, we are saying that if you have any distinct vectors, right, well, you have to do it in sort of by contradiction, right? You have to say that suppose that this thing was linearly dependent, then you would be able to find a subset for which it would be linearly dependent. Okay, so this direction I'm going to leave as homework just for you to clarify for yourself, but it should be relatively straightforward. Okay, and the idea is to do it by contradiction. All right, thank you, Tej. That's been helpful. Does somebody else want to take over from Tej? Otherwise, we'll have to keep Tej around. Any volunteers? You guys, come on, don't be shy. I know many of you are following along. I know not all of you are doing it, but okay, so we'll do one more section and then maybe we can ask again if nobody's volunteering. Okay, so now we look at the definition of a vector space. A definition of a basis. So let V be a vector space. A basis for this vector space V is a linearly independent set of vectors in V, which spans the vector space. Okay. So we already defined what linear independence is. So now the basis is basically you take a bunch of vectors, ensure that they're linearly independent, and they span the vector space. So these are the two conditions. Condition 1, independence, and condition 2 is that they span the vector space. Okay, if that is the case for any set of vectors, then we would say it is a basis. And the space V is called finite dimensional if the set V is finite, the basis is finite. Is the definition okay? Tej.
Yes, sir.
The definition's fine? Okay. All right, Tej. I think I will ask you to nominate somebody to volunteer after this example, okay? Right, so let's go through example 12. So example 12 says that let F be a subfield of complex numbers. In F3, let's consider these vectors, okay? Okay, so these are, you can see the vectors, and the claim is that these vectors are linearly dependent because it turns out that they satisfy this equation. Okay, so if you take 2 times alpha 1, whatever this equation is, you'll get 0. Okay, so this is don't even want to put it as homework. Okay, so this is something you can check. And these vectors epsilon 1, epsilon 2, epsilon 3 are linearly independent. Okay, why are they linearly independent? So you can try writing it, right? You can say C epsilon 1, C2 epsilon 2 plus C3 epsilon 3 is 0, right? And what this would mean is that you have C1, C2, C3 equals 0, 0, 0, right? So the only way you can satisfy this is if all C's were 0, right? So therefore this is linearly independent. Okay, good. All right, Tej, you have to nominate somebody because people are not volunteering and I don't know who to ask.
I'd like
Do
to
you have
ask
any
Manan.
suggestions? Okay. Manan, could you please unmute yourself?
Yes.
Okay, thank you so much, you guys. All right. So example 13 does the following. So let F be a field, okay, and in Fn, let S be the subset consisting of these vectors, which are defined as follows. Okay. You're following along, right, Manan?
Yes, sir.
Yeah. Okay. Keep yourself unmuted. Okay. Don't hesitate. So that there's
Okay.
otherwise there's too much lag when I'm asking and getting a response. Okay. So now let x1 to xn be scalars in capital F, and we put alpha equals this linear combination, right, with the weights xi's and the vectors epsilon. Then it is clear that alpha is this object, right? Is this okay?
Yes, sir.
Okay. And this shows that epsilon 1 to epsilon n, it spans Fn. Right? Because, so what is the definition of Fn? Fn is just a bunch of coordinates, right? It's arbitrary x's. And alpha can have arbitrary coordinates here, right? Is that okay? Manan?
Yes.
Are you okay? Okay. Sorry, yeah, there's a little bit of lag, so I couldn't tell. All right. Now, since alpha is 0, if and only if x1 to xn are 0, right? That is the only way that we get the 0 vector. These epsilons are linearly independent, right? So it's exactly what I said above here, right? It's basically just saying this thing. Is that okay?
Yes, sir.
All right. And the set S is accordingly a basis for Fn. And we shall call this particular basis the standard basis. Okay, so that is sort of the whole point of this example, that we're introducing something called a standard basis. Okay, so this thing is going to be a standard basis. All right, now let's look at example 14. So example 14 starts getting a little bit more interesting. So example 14 says that let P be an invertible n cross n matrix. Okay, so we have a matrix P with some entries. It has n rows and n columns in some field F. Okay, and let P1 to Pn be the columns of this matrix. Okay, so P1 is the first column, P2 is the second column, and so on. And Pn is the last column. Now the claim is that these P's, so Pi, form a basis for Fn cross 1. Basically, it forms a basis for all the columns. Okay. So is the statement clear?
Could you please again explain this?
Yeah. So the statement is that you consider an invertible matrix. Okay, so that is the important part. So consider P such that P inverse exists. Okay, and we write P. It's an n cross n matrix. We write it in terms of its column. So P1 to Pn. Okay, and we say that, and the claim is that. So this is fine, right? I'm just writing it as columns. P1 to Pn.
Yes, sir.
Is that clear? Yeah. Okay. And now the claim is that if you take these PIs, they form a basis for all column vectors.
Okay.
So that is the statement is clear at least, right?
Yes.
Okay, so how do we prove this? So what we want to argue is that whatever suppose we take y, so suppose y is some arbitrary element in Fn cross 1. We want to show, right? We want to show that y can be written, right, as a linear combination of Pix, right? Because that is what it means to be a basis, right? So we have to establish two things, right? That we have to establish that these Pi span Y. So that is the spanning property. So let's look at the definition, right? Let's look at the definition again. Right. So there were two properties, right? One we had to establish was that it spans the space, and the first was we had to establish that it's linearly independent, right?
Okay.
And to span, we know that, so this we discussed already. To span means that you can write any y as a linear combination of Pi's. That is the spanning property, right? And the first property was what? That Pi's have to be have to be linearly independent. Correct? I'm just writing down what
Yes.
the definition is. Okay, so let's see how the example solves it. So the example says, let us do the following. So let X, so suppose X is a column matrix. Okay, then one can write P times X as follows. Okay, so it is just expanding out the matrix, right? So we're writing P1, P2, and so on, Pn, right? If you're multiplying it with x1 all the way to xn, right? We're just doing matrix multiplication. This will give you x1, p1, and so on, xn, pn. Is that right? So the
Yes.
statement is it okay? All right. And then px equal to 0 has only the trivial solution x equal to 0. Yeah. So this is the trivial solution, right? Somebody was asking in the beginning. So the trivial solution we had discussed in the context of linear equations, and we showed that. So you have to recall that P is invertible, right? We had shown in one of the theorems that this is equivalent to saying that Px has only x equal to 0 as solution. Do you remember this?
Yes, sir.
Manan? This is one of the theorems, right? We discussed it at length in class, right? So
Yes.
using that theorem, what we get is that the only way that Px equal to 0 would happen is if x was identically 0. Okay.
Okay. Yeah. But don't we need to prove that P is invertible?
Okay, so look at the premise of the question.
Oh, okay. P is invertible.
Right? So we're already assuming P is invertible, and under that assumption, we know that the only way this can be satisfied is if x is 0. So far you're with me, right?
Yeah. But don't we need to show that first x1, each xi is equal to 0?
Yeah, so what is this capital X equal to 0? So what does this notation mean? This notation means that the vector x1, not the vector, the column, right, is going to be equal to this, right? This is what it means for a column to be 0.
Okay. Okay. Understood.
Right? Okay.
Yes.
So okay, so perfect. And then now what does Px equal to 0 mean in terms of this? It basically means that this has to be 0. Right?
Yes.
Okay. Because the only way that you will get 0 is if, sorry, okay, I messed up. So this statement is saying that the only way sum over xi pi is 0 is if xi is 0 for all I. Correct? Is the statement clear?
Yes.
Okay, so and then what does this say? It tells us, so what was the first property you wanted to show here, right? So are you convinced that this point that I've highlighted is now proved?
Yes, sir.
Right? Because to show linear independence, we just have to show that the only way to get this 0 is if all the x's are 0, which is what we've done. Okay. So part 1 is done. Part 2 is asking what? It's saying we have to show that it spans, right? We have to show that for any y, I can write y as a linear combination of pi's, right? That would mean that using pi's, I can span the space of Fn cross 1. Is that okay?
Yeah, but P can be any column matrix. So isn't it already spanning the F in cross 1?
No. So P is given to you. P is fixed. Okay, so this is fixed. So you're given one fixed matrix, and using the columns of this matrix and taking the linear combinations, we want to argue that you can get to any y, any element in Fn cross 1.
Oh, okay.
Right? Okay, so how do we do this?
Yeah.
Well, we say that, okay, so the problem is clear.
Yes, sir.
Okay, and how do we show this? We show it by proceeding as follows. So we say if capital X, so we say let capital X be defined as P inverse of Y. Okay, so we know P is invertible, so P inverse is well defined, correct?
Yes.
And Y is given to us, right? Y is arbitrary, so we can always define X to be this object, P inverse of Y. And this would imply that y is basically just p times x, correct? Because p is invertible, I can multiply on both sides by p. So multiply
Yes.
by p on the left, right? And then this one can write as what? One can write it as xi pi, sum over I, correct? Just this
Yes.
expansion here that we had, right? Okay, and so what does this tell you? It tells you that regardless of what y you chose, I can write it as a linear combination of pi's, right? Because x is, so these are the coefficients. So this is what the c's were in the discussion earlier. This is what we were calling alphas, right? Okay, so I'll give you
Yes.
1 minute to make sure that everything sort of makes sense for others also, because yeah, it's either completely trivial for you, or if it's the first time you're seeing it, then you maybe take a minute, make sure you're following. Okay. Any questions? All right. Manan, do you want to nominate somebody to follow along next?
Uh,
Hello,
Rishabh.
Rishabh. Okay. Rishabh, can
Yes, sir.
you please unmute yourself? Rishabh, are you on the call? I have a. Rishabh, your hand is raised, but I can't hear you. Okay, I think you unmuted yourself now. We don't hear you for some reason. Can anyone else hear him? Manan, can you hear Rishabh?
No, sir.
Okay, so Rishabh has some technical issues, it seems. Do you want to recommend, sorry, nominate somebody else, Manan? Should give me a second. There's always some delivery thing that happens. Just a second. All right, I'm sorry for the inconvenience. All right. Manan, did you think of somebody?
Sanath.
Sharat, can you please unmute yourself? Is he online, or are they online? I don't know. Okay, somebody has to volunteer, otherwise it's difficult to proceed.
Hello, sir.
Hi, can you identify yourself?
Jayant.
Jayant, okay. Thank you for volunteering, Jayant. You saved the class. Otherwise, you would have gotten stuck. So thank you. Right, so let's continue then. Okay, so example 16 is basically an example that considers infinite bases. Okay, so let F be a subfield of the complex numbers. Okay, and let V be the space of polynomial functions over capital F. Okay, so polynomial functions, remember, are of this form, that you have some coefficients and you have some over with the different x's, right? Is this okay? The definition, is
Yes,
this
sir.
fine? Jayant, thank you. All right, and then we can define f sub k to be oops, it's supposed to be x to the k. Okay, so it's x to the k for k equals 1, 0 to 0, 1, 2, and so on. And the claim is that the infinite set f0, f1, f2, and so on is a basis for V. Is that okay?
Okay.
All right. So the claim is fine, right, with everyone. So what we're doing is we're looking at, so what is the space V? It is the space of polynomials over F. And the claim is that the infinite set of f0s to f2 is a basis for V. Okay. Is the claim fine, Jayant?
So could you just explain once more about how the basis works? I didn't understand it the first time.
How the sorry, say your question again. What is the question? What the definition of the basis is?
Yeah, I didn't
Okay,
quite
yeah.
understand it the first time.
No worries, yeah. So let's see. Okay, so this is the definition of f sub k. No, okay, let me write down. Sorry, this is the definition of f sub k. Okay, so using this definition, what is f sub 0? Oh, f sub 0, okay. Is what?
C0?
No, this is the definition. F sub k, this
Oh,
here,
1, 1. Sorry.
right? F is, okay, so what is f1?
X.
Exactly, okay, and so on. So fk of x is x to the k, right? That is the definition. And what is the claim? The claim is that there is some vector space V, right? The vector space is just the set of polynomial functions over F, okay? And
Yes.
the claim is that these things, we'll treat them as vectors, okay? So I'll think of this as alpha 0, alpha 1, alpha k. Okay, and the claim is that alpha 0, alpha 1, alpha k, these vectors, they form a basis. Okay, so there's no k root, so it's infinite. That's the whole point. Sorry. So this is a basis for polynomials. Okay, if you treat polynomials as vectors, as a vector space V. Is the claim okay?
Yes, sir.
All right, thank you. Yeah, this is very helpful, right? It's good for me to know that when things are and are not clear. Okay, so why is that? So what are the two things that we need to show that something is a basis? So there were two things, right, that we showed in the previous example. So one of them was that we had to show that alpha i's are linearly independent, right?
Yes, sir.
And the second was what? Do you remember?
The, um, they you can form you can get any y for all values of the vectors.
Right. So what we want to show is that the span over alpha I, if you use this thing, it gives you V. Right? That you can essentially reach any vector in the vector space by taking some linear combination of alpha i's. Right? So those were the
Yes, sir.
two requirements. Okay. So it says clearly the set spans V, right? Because one can write F as C0, F0, C1, F1, Cn, Fn, right? Because so F0 is what? F0 was?
1
F1 was?
x
Right? And Fn is?
extra for of n.
Exactly. And what is the definition of Fx? It is identical, right?
Yes, sir.
So clearly one can write, so clearly these Fk bases, it clearly spans the set of all polynomials, right? So it spans V. What we need to establish is that these f0s are independent, right? So f0, f1, f and so on, they are independent. And it turns out that to show that this infinite set is independent, it is enough to show that any finite subset is going to be independent, right? So this is what we proved in one of the properties, right? Right? So property 4 was what? It was saying that to show that a set of vectors S is linearly independent is equivalent to showing that every finite subset is linearly independent. Correct?
Correct, sir.
Okay. So that is what we're going to use now. So consider any subset, any finite subset. Okay. So suppose we look at this finite subset. This is exactly the same as saying that, you substitute F0, Fn, and you get this equation. Correct?
Yes, sir.
Okay. And now this in turn, what does this equation tell us, right? So this equation says that it has to be 0 for all x in the field, right? This is what it means for this vector to be 0, right? That regardless of what x you choose, this is 0. But you will recall that for a polynomial of degree n, it can have at most n distinct roots, right?
Yes, sir.
And here it is being claimed that it has essentially as many roots as there are elements in the field. And this field we took to be a subfield of complex numbers, right? So this is essentially infinitely many elements. Okay. And so that what that means is that the only way this can be 0 is if all the c's are 0. Right?
Yes, sir.
All right. And what does that mean? It means that these vectors, right? So what was the definition of linear independence?
They all
Linear
go
independence at
to 0.
exactly. So the only solution that one can find here is if all c's are 0. Okay, so that is what linear independence meant, and that's exactly what we have here. Okay, so we've established that these FIs, F0, F1, and so on, they form a basis for V. Is that okay?
Yes, sir.
Okay, perfect. You were Rishabh, right? No, not Rishabh.
Giant.
Jayant, yeah. Okay, Jayant. So it makes sense, right, Jayant?
Yes, sir.
Okay, perfect. All right, so let's continue then. So remark 1 says, could V have a finite basis? Okay, so now we're asking, we had an infinite basis, right? We just showed that there is an infinite basis, F0, F1, and so on until infinity. Can we have a finite basis, right? It does not necessarily mean that V does not have a finite basis. We showed one basis. It could be that, there's maybe a finite basis, right? It's not at least immediately clear to me. Is it clear to you that it could have, it cannot have a finite basis?
There are some specific conditions it's possible for it to have only a finite number of elements.
Sorry, your voice is not very clear. Say it again. Get close to the microphone, maybe.
Sir, there are some other conditions it might make them.
Yes, it's
It
not
might
clear,
make it
right?
a finite basis.
Right. It's not clear. It's not clear a priori, right? That just because we found an infinite basis, that they cannot be a finite dimensional basis as well. It turns out that it cannot. So we cannot have a finite basis, right? As it says here. And this actually turns out to be true very generally. So we'll prove it in the following theorem. But let's look at this specific example and see why is it that we cannot have a finite basis. Okay.
Okay, sir.
So, right. So suppose that we have a finite number of polynomials. So G1 to GR. Okay. If you have a finite number of polynomials, right, then there would be some largest power of x, right? Because these are the finite number of polynomials. Each polynomial has some maximum degree. And suppose that this highest power is k. Okay, so like there's x to the k is the highest order term that appears in any of these polynomials. Is that okay?
Yes, sir.
All right. Now, clearly, one can define fk plus 1x. Sorry, one can recall that fk plus 1x was defined as x to the k plus 1, right?
Yes, sir.
And that is clearly not in the span of G1 to GR, right? There's no way that you can produce xk plus 1 using a linear combination of lower powers, right? That just isn't. Okay. So therefore, we conclude that we cannot have a finite basis, because if it did, then we reach a contradiction that the basis will not be able to span all elements of the polynomials or the space of polynomials. Is that okay?
Yes, sir.
Sure?
Sorry,
You're
sir.
sure, right? There's no, okay, sounds good. All right. So all right, so V is not finite dimensional. All right. So now we come to the theorem. So theorem 4 says the following. So it says, let V be a vector space that is spanned by a finite set of vectors, beta 1 to beta m. Okay.
Okay, sir.
So suppose that this is the case, that you can span it using some beta 1 to beta m. Then any independent set of vectors in V is finite and contains no more than m elements. Okay, so the statement is saying that regardless of which independent set you pick for this vector space V, it will have to be finite and it cannot contain more than m elements. Okay, if you're given that the vector space is spanned by a finite set of vectors. Okay, so let's try to prove this. Yeah, maybe do you want to recommend, sorry, nominate somebody else? Oh, wait, what was your name? I keep forgetting your name. Jayant, do you want to recommend, sorry, nominate somebody else? Or if somebody else wants to volunteer by themselves, that is also fine. Jayant, does any name come to mind?
I'm not sure, sir.
You're not sure? Okay. I'll let you guys, somebody has to volunteer.
That's fine. We can continue.
Mhm.
Professor.
Hi, can you identify yourself, please?
Emmanuel.
Emmanuel. Hi, Emmanuel. So thank you for volunteering. Let's continue. Right. So theorem 4, the statement, is the statement clear for theorem 4? Yes. Is there a question?
I have a small question in the previous ones.
Okay. Tell me.
Yeah, so basically said that using the function we can never produce x plus g onto g. We can never produce a term which has higher power.
I am sorry,
X
your voice
itself
is
is a
not.
scalar.
I cannot understand the question very well. The connection seems to be a bit unstable somehow. Is it for everyone or is it just for me? Emmanuel, can you hear the question clearly?
Not quite.
Okay, do you want to say the question again, please? Who was I talking to? Can you identify yourself, please?
Is it better now? My name is Aka.
Aka?
No,
Okay.
Ambik.
Ambika. Okay. I heard Ambi this time and Aka last time, so I'm guessing it's Ambika probably. Okay.
Okay, so basically we like terms containing x power 0 to x power k, we can never form a term which contains x power k plus 1, right?
Yes.
But can we not say that x in itself is a scalar, because we are considering functions which can only scalars as inputs. So x in itself is a scalar, so x into x power k plus 1, right?
I am not sure I fully understand what you're saying, partly because of the connection. But it looks like an isolated thing. Maybe you can ask me after the class. Would that be okay? Because I think it'll need a little more discussion and the connection is very unstable, unfortunately. But okay, just to quickly say, we are treating these things as vectors. Yeah, so yeah, okay, let's do it after the class then. I think that might be easy. Okay, so Ambika, you can email me, okay? So this is a to-do for you.
Yeah.
Okay, you can email it and then we can sort out. Okay, all right, any other questions? All right, so let's continue then. So Emmanuel, is the theorem statement clear?
Yeah.
Okay, perfect. So let us continue then. So all right, so we're looking at the proof now. So the proof strategy is as follows. So we're going to prove so to establish the theorem, it is enough to show that every subset S of V contains more than m vectors is going to have to be linearly dependent.
Yeah,
Right?
that makes sense. The contrapositive.
Exactly. All right, so let's start then. So suppose S is some subset of V, right, containing n elements where n is strictly greater than m. Okay, and these are, we call these vectors alpha 1 to alpha n. So this is fine.
Yeah.
Okay, and then
Yeah.
since beta 1 to beta m, they span the vector space V, right? So in the premise, right, we were given that beta 1 to beta m, they span the vector space V,
Vector
right? So
space.
that is what we're writing. Exactly. So since beta 1 to beta m, they span the vector space V, there exist scalars AIF in the field such that this is true. Right? So for each alpha, so for the jth alpha, one can write it as a linear combination of betas. Okay, and we are just calling the coefficients Aij. Is that okay?
Yeah. Yeah.
All right.
This makes sense. Just linear combinations.
Exactly. And then for any scalars x1 to xn, we have the following. So we have that you take a linear combination of x1, alpha 1, and so on, right? So we're just taking linear combinations of alphas. Okay, so I'm just rewriting it, right, as just a sum. So this is fine. Is the first step okay? This is just sum.
Yeah. Just summing up.
Some notation, right? So it's the same thing. Okay, and then the next step, what are we saying? We are substituting for alpha sub j using this. Okay.
Yeah. Right.
So this is just substitution. So this step should also be fine. And now we are just regrouping terms, right? So we are regrouping the terms. So now we're going to do, because everything is linear, right? So we can change the order.
Yeah.
And okay, so we have this. So now what we're going to do is we're going to and we haven't changed the order of the sum actually. Yeah. So you just push xj inside, and then we continue with the sum. And now we change the order of the sum, right?
Yeah.
And these are all finite sequences, so there's no problem. And when you sum them, right, what do we get? We get
It's a matrix AX.
yeah, so this is just the matrix AX equals B. Okay, so far everything should be fine, right? So from this step to this step.
There's a person with a doubt.
Sorry, what?
This person with a doubt. Manan has a doubt.
Manan has a doubt. Yeah, you guys please speak up, okay? If you have a doubt, I'm sorry, I cannot, since I'm not
Yes.
looking at the screen,
So,
I don't see that.
So how can we say that alpha j is equal to a linear combination?
Alpha j is
Above.
No, we are considering, right? So we are saying that you take any of these scalars, and if you want, you can say and consider this expression, right? So we are just taking
Okay.
a linear combination of. We are just looking at this expression, and we're going to reason about it, right? And what we want to reason is that
Okay.
if you have more than if you have n elements, where n is greater than little m, then we'll show that this linear combination can always be made 0 with non-trivial entry. Something like this is what we want to argue, right? Because we want to show that if you have more than n vectors, more than little m vectors, then it's going to be linearly dependent, right? That is the strategy we're trying to follow. So to implement the strategy, we are going to consider a linear combination of these alphas. I'll give you a moment just to make sure that you're following. Okay, take a second. All right. Is it okay? Does it make sense?
Yes, sir.
Manan? Okay, perfect. So then let's continue. Now, what do we know? We know that, so we're going to recall theorem 6, right, from chapter 1. So theorem 6 said that if A is an m cross n matrix, so m is the number of rows, n is the number of columns, and it is the case that the number of rows is strictly smaller than the number of columns, then the homogeneous system of linear equations only has a non-trivial solution.
Yeah.
Yeah, so this is sort of like a longer matrix, right? The number of columns is higher, so you can always like sort of embed, there's the row
Yeah.
echelon form, and then the rest can be whatever, doesn't matter. So you can always, so this part allows you to invert it. Okay.
Yeah.
Now, since little n is strictly greater than capital M, okay, so theorem 6 says that there exist scalars, right, which are not all zeros, such that this equation will be zero.
And
Right?
we're
That is
justified
what
in
it means
taking,
to.
yeah, we're justified in taking this choice of x-ray because earlier we stated that we could do this for any scalars. We're just taking a particular case, right?
Exactly. So here we when we started, we said, okay, consider some arbitrary scalars. Now we are choosing those scalars. We are saying that this theorem tells us that there exists some choice of x's such that this linear combination will disappear. Okay,
Right.
and not all zeros. Okay, all right. And so now we can use this fact, and if you plug it here, it means that this sum is going to be zero.
Yeah.
Right? Okay, and then what does that mean? Zero times, well, you sum zero a bunch of times, you still get zero, correct?
Yeah.
So in effect, what we have is that this equation, right? This equation is going to give you a zero.
Yeah.
Right? So there exists a choice of x's, not all zeros, right? Such that this combination, this linear sum, this linear combination disappears. And well, this was the definition of being linearly dependent, right?
Yeah.
All right. So what have we concluded? We've concluded that if you have if you have a set with more than strictly more than m vectors, then they have to be linearly dependent, right? So that's essentially what we proved in general.
Yeah.
That the set S is linearly dependent. Okay, and that was enough to show the theorem, which was saying that if you have m many finite vectors, then any independent set of vectors that is finite will have to contain at most m elements. It cannot contain, any linearly independent set has to contain at most m elements. It cannot contain more than m elements. All right?
Yeah.
Perfect. Thank you. Right, so maybe let's do the corollary as well, and then maybe we can ask somebody else to volunteer. So corollary 1 is now saying the following. So if V is a finite dimensional vector space, okay, then any two bases of V have the same finite number of elements.
Yeah.
Okay, so it's sort of intuitive, right? Because you have to be able to span it and you have a bound on the number of elements. So let's see how the proof works. The statement is clear, right, Emmanuel?
Yeah. Yeah.
Okay, perfect. If anybody has any questions, please feel free to ask, right? Because everyone has like slightly different preparation, so things may go faster or slower depending on who's volunteering. So if you have questions, please don't hesitate to ask. Okay, so let us continue then. So since V is a finite dimensional, since V is finite dimensional, it will have a finite basis, right? Because that was the definition of being finite dimensional. So recall definition of finite dimensional. Okay.
Yeah.
So it's just basically rewriting the definition. Now, by theorem 4, right, we have that every basis of V is finite and cannot contain more than m elements.
Yeah.
Correct?
Yeah.
Okay. And so what that means is that suppose alpha 1 to alpha n is a basis, then it must be the case that n is at most m. Correct?
Yeah.
Perfect. And then one can run the same argument backwards with basically alphas and betas flipped. Right? So one can argue that if alpha is a basis and beta is another basis, then beta can have at most n elements. Right? So that would mean m is at most n. And so therefore we conclude that m has to be exactly n.
Yeah.
Right?
So it's just like all those group theory proofs where you prove that there's only one unity in a group.
Right. Yeah, that part I don't even remember. So that's good. It's good that you know more. Fantastic. All right. Is the proof clear for everyone? Okay. Let's see. All right, Emmanuel, do you want to nominate somebody?
Let me just take a look.
Yeah, you can look at the list of people who are online if you think somebody maybe, or if somebody is willing to volunteer themselves, please speak up as well. That is perfectly fine.
We shall nominate Ashwin Arvind.
Arvind, is that what you said?
Ashwin Arvind.
Okay, I am not fully sure I'm catching the name, but if you are online, could you please
Ashwin.
speak up?
Ashwin Arvind.
Ashwin.
Yeah. Yeah.
Ashwin, okay. Ashwin, could you please speak up if you're on the call and if you're following along? Samarth has his hand raised.
Hello, sir.
Hi, do you want to volunteer or do you have a question? Or
Sir, I have a question.
okay, yeah, next time just speak up, okay? Because it's just by chance that I saw the hand. Yeah, tell me, what is the question?
Sir, in Theorem 4, how you have used that Theorem 6? Can you again explain that part?
For sure. Okay. So until this step, this equality we were fine, right? Is that okay? This step over here.
Yes, sir.
Okay. All right. So so we know that we are taking an arbitrary linear combination of alphas, right? And we know that this we can write in the following form, correct? You can
yes,
stay
sir.
unmuted. Yeah, stay unmuted. So I sort of know whether things are making sense. If
Sure,
that's
sir.
okay, of course. Okay. Right. So we have this form, right? And now what we want to argue, the idea is that we want to argue that this linear combination is 0. This is what we claim. Okay.
Yes, sir.
And the point is that if we are able to claim this, then we know that claim this is 0 for some choice of x's.
Yes,
Right?
sir. Linearly
So if we
independent, yeah.
Exactly. So if we can show that for some choices of x, this thing disappears, then we know that this entire thing is linearly dependent, right? Exactly what you were saying. Is that
Yes, sir.
okay? All right. So it basically remains to establish that this object is 0 for some choice of x's. Right?
Yes.
Okay. And this actually turns out to be the case because we can use theorem 6. So theorem 6 was saying that if you have a matrix A that has more columns than rows, okay? So a matrix like this, like it's a
Yes,
long
sir.
matrix. So n is, this is m, and we have m is strictly smaller than n. So the number of columns is higher. Then we know that the homogeneous system of linear equations has a non-trivial solution.
Yes, sir.
Okay, so there exists some x, which is not all zeros, which will give you, upon multiplication with a, it will give you 0, right? And so we basically get the fact that this claim, right, we basically prove it using theorem 6, that this ax will disappear for some choice of x.
Yes, sir.
Right? And then you already agreed that once we can establish that this is 0, we conclude that the linear combination is going to be 0. And if the linear combination is 0, then we've concluded that the set is linearly dependent. Right?
Yes, sir. But what are the elements of the matrix m cross n? How are you making the matrix?
Yeah, okay. So that comes from the previous step, right? So what we are given is so in the question, what are we given? Sorry, in the theorem statement, what are we given? We're given that there is some vector space V which is spanned by some betas, beta 1 to beta m. Okay.
Yes, sir.
And now we are considering some subset V of vectors that are, whatever, they are arbitrary vectors, alpha 1 to alpha n. Now, because we know that beta span the space, we can write alphas as linear combinations of betas, right? So for each alpha j, I can write a linear combination in terms of the betas, correct?
Yes, sir.
So it is these coefficients that are forming the matrix A.
Okay.
Okay, and this matrix itself will allow us to compute these x's. such that we can show that there's a linear combination of these alphas that are 0. Okay, does that make sense? I'll give you 1 minute to
Okay, sir.
process what you've understood, and then we can move on.
Sure. Sir.
All right. What was your name? Samarth, is it?
Yes, sir. Samarth.
Okay, so I hope you are satisfied. It makes sense.
Yes, sir. Thanks.
Okay, perfect. Any more questions? Okay, Samarth, since nobody else is volunteering, do you mind staying on and helping me, volunteer to follow along? Is that okay?
Sure, sir. Yes, sir.
Okay, thank you so much. Okay, so let's continue then. So now the story is that this corollary allows us to define the dimension of a finite dimensional vector space. So, excuse me, the definition of dimension of a vector space for a finite dimension is the following. So it is the number of elements in a basis for V. Okay. So it is the,
Yes, sir.
you basically take a vector space, right? And the previous theorem was saying what? It was saying that regardless of what basis you take, the number of elements in the basis are going to be the same, right? That's what the corollary is saying. Right? Is that
Yes, sir.
is the statement of the corollary clear?
Yes, sir.
Okay. So the corollary, and also you don't have to say sir, but okay. That's like true for everyone in general. Yeah, this thing is not needed, but okay. So the point is that so this allows us to define a notion of dimension. And the notion is that you take any basis, and the number of elements in this basis is going to be the dimension of the vector space, at least for finite dimensional cases. Okay, and we know that this is unique because the corollary shows that regardless of what basis you choose, the number of elements in all the bases are going to be identical. Okay, and so the dimension of V is given by, so we use this symbol dim V for the dimension of V. This is just the definition. Is this clear?
Okay. Yes, sir.
Okay, perfect. Right, so now let's continue. So using this, one can reformulate theorem 4 as follows. So one can write, so we are writing theorem 4 as a corollary now. So we're saying let V be a finite dimensional vector space and let n be the dimension of V. Okay, and then any subset V that contains more than n vectors is linearly dependent. Right, this V essentially is what we showed above. And also, no subset of V contains fewer than n vectors can span V. So you cannot span V with fewer than n vectors, right? Where n is the dimension of the vector space.
Yes.
So these are basically just a restatement of the facts that we established above. All right, now let's look at an example.
Yes,
So example, nice. So now let's look at an example. So example 17 says the following. So if F is a field and the dimension of F to the n is little n, oh, sorry, I messed up. Okay, so if F is a field, okay, then the claim is that the dimension of F to the n is little n. Okay, it's just a very, very quick example. And why is that? Wait, what was your name? I forgot. Samarth, why do you think that is?
Sir, can you again repeat it? There wasn't. I couldn't listen.
No worries, no worries. Yeah. So the
Example
statement
7.
is that, yeah. So example 17. So I'm looking at this part, right? So the example is asserting that suppose F is some field, okay, and we consider F to the n. Then the dimension of F to the n, the claim is this is going to be n, because that's what the example is asserting. So I was asking, can
Yes,
you
sir.
prove this? Do you see how that might be the case? Do you have any idea how one might show
So
this?
the basis of so the statement is saying that the dimension is n because the standard basis for f to the power n contains n vectors. So
Exactly.
we proved it above na ki this is the definition of dimension.
Exactly.
If the basis contains n elements, then that
Precisely. Very good. So the way they're proving it is they're showing that look, here's a basis for this f of n, and this basis contains n vectors, right? And the basis is this, right? This is what we saw. It's a 0, 0, 1, 0, 1, 0, 0, right? Sorry.
Yes, sir.
This is the standard basis. And we already showed that these are linearly independent, right? These are linearly independent, right? And they span the space.
Yes,
This we
sir.
showed in one of the previous examples. And this implies they're a basis, right? And that in turn implies the number of, or the size of the basis, right? Size of the basis is the same as the dimension of the space, right?
Yes, sir.
Okay. So exactly. Okay, so it's a very simple example, but it's good to sort of make at least trivial things completely trivial. So there should not be any mystery associated with them. Okay. Can we continue, Samarth?
Yes, sir.
Okay. All right. So then the matrix F m cross n has dimension mn. Okay. Do you see this?
Yes, sir.
Right. So the idea is it's very similar to how we did it for the Fn case, right? Because you just contain mn matrices, m times n matrices, and each matrix has like zeros everywhere, except the ith row and the jth column, right? This is one, and it zeros everywhere else, right? So you consider such matrices. How many such matrices are there? There are n choices for I, n choices for n. So you have mn such matrices, right? And using these matrices, just as we did in the case above, you can both show that they're linearly independent and that they can span the space, right?
Yes, sir.
Okay, and so therefore they form a basis, and therefore the dimension is m times n. Is this clear? You seem to
Yes,
be
sir.
hesitating. I don't know if you're okay. Sounds good. All right. And then if A is an m cross n matrix, then the solution space for A has n minus little r. The solution space for A has dimension n minus little r, where little r is the number of non-zero rows. Okay, so this is so this part I'm going to maybe put it as an assignment. Okay, because it's related to example 15 that I sort of skipped for now, so I think I'll leave that. Example 15 was earlier. Okay, but the idea is very similar. You're basically just going to look at the number of. You're basically looking. You're going to look at the basis, and then using the basis, you can conclude what the dimension should be by the number of elements in the basis. All right. Okay, so we have about 10 minutes. Okay, so Samath, do you want to nominate somebody else who might be interested in volunteering? Otherwise, I might have to ask you to stay on, which I don't want to because you've already been kind enough for a while.
Sir, I
Yeah.
guess Ashwin, Arvind, if
Ashwin, yeah, we asked him earlier. I don't know. He wasn't either. Either there is some problem with his equipment. We couldn't hear him. Ashwin, can you hear us now?
so then I don't know actually.
Oh, okay.
Who should I?
Okay, let me ask one more person. Maybe Ambika was it, right? The person who was asking a question. Ambika, do you want to volunteer to follow along? Oh, but her connection was bad. That was the problem. I still can't hear you. Okay, so maybe Samarth, maybe can you, is it okay to continue for 10 more minutes? I don't want to waste too much more time.
Sure, sir.
Okay, thank you. All right. So the remark now is that the zero subspace has dimension 0 by convention. This part is sort of very straightforward. There's nothing very deep happening here. So what we are arguing here is that if V is any vector space over F, okay, the zero subspace of V is spanned by the vector 0. Okay.
Sir.
That is just essentially
Yes,
the definition, right? Like it just has the zero vector. That is the vector space.
So zero
However,
subspace means the subspace. Hello. Yes.
Yeah.
Excuse
Go
me,
on.
sir.
Yeah. Go on.
So zero subspace means the subset contains only vector 0.
Yeah. Exactly. So that is all there is.
Okay.
Yeah. Because you can take C times 0, and this will still give you the 0 vector, right? That is just the definition. So it satisfies all the other properties, and it is indeed a vector space, right? It's a trivial vector space, but nonetheless, it's important to sort of settle on what we mean by dimension of the 0 subspace. And the point is we'll take it to be 0 by convention. And here we're just justifying why that is. So, all right. So however, 0 is a linearly dependent set, right?
Yes, sir.
So why is 0 linearly dependent?
Because it is satisfying the property C dot 0. Matlab, we can find a linear combination.
Exactly.
We can find such vectors where the linear combination is 0.
Exactly, because for example, 1 times the 0 vector is the 0 vector, right? So it is evidently a linear combination. Actually, a non-trivial. Okay, let me just say a non. Yeah, okay, fine. I'll just keep it at that. It's okay. All right. So for this reason, we simply say that the 0 subspace has dimension 0. Okay, because normally what we were saying was that you have to take a basis, right? And then the basis has to, the size of the basis is going to give you the dimension of the space. But the point here is that there's only one element in the set. And if you take that element, that is also not linearly independent, right? That is linearly dependent. So our standard way of defining the dimension does not really apply here. Okay. And there is some more discussion. I guess I'll leave this part also as just reading. You can take a look at it at home. So let's use the remaining few minutes for the next lemma. So now this lemma is saying the following. Is that okay? Wait, who was I talking to?
Yes,
Samarth,
sir.
right? That's
Yes.
okay, right? Okay, fantastic. I'm sorry I'm writing your name again and again because I forget. So this helps me keep track. All right. So the lemma says the following. So let S be a linearly independent subset of a vector space V. And suppose beta is a vector in V which is not in the subspace spanned by S. Okay, so what is it saying? So S is a linearly independent subset of the vector space V. Okay, so S is linearly independent and it is a subset of the vector space V. And we're saying suppose beta is a vector in V, right? That is not in the span of S. Okay.
Sir, beta is a vector in V. Matlab, this means that beta is does not belongs to S.
It does not belong to the span of S. So yeah, this is so beta does not belong to
Okay.
span of S. Exactly. Okay. So let's be more clear. Let's remove this. Right. So there's S is some linearly independent set. S is a subset of V, and beta belongs to V, but beta does not belong to the span of S. Okay. So the premise is clear.
Yes, sir.
Okay. So now the statement is that the set obtained by adjoining beta to S is linearly independent. Okay, so what this is saying is that if you take beta and you take union S and you consider this set, so it says that this set stays linearly independent. Right, so it's not clear. If you add a new vector to an existing set, it might become linearly dependent, right? For example, if I have, I don't know, alpha, beta linearly independent, and I add alpha plus beta, right? Now this new set is no longer linearly independent, right?
Yes, sir.
Yeah, so let me write it. So I'll say, for example, if alpha, beta, yeah, let me write it as sets because that is easier, is linearly independent, then alpha, beta, gamma may not be linearly independent. And you can take, for example, gamma equal to alpha plus beta, right? So this is entirely possible that it becomes linearly dependent. But here the claim is that even if you add this new vector beta, the set will continue to stay linearly independent. Okay, is the statement clear?
Yes, sir.
Okay, so let's see if we can do the proof in the next few minutes. So suppose that alpha 1 to alpha m are distinct vectors in S. Okay, so S is this subset that we started with. So suppose that these vectors are labeled by alpha 1 to alpha m. And it so happens that there is some linear combination of these vectors in S and beta, right? such that the linear combination gives you 0. Okay, so we're
Yes, sir.
basically we're trying to do a proof by contradiction.
Yes, sir.
Right, so we are saying that, okay, let's assume that what the theorem is saying is not true. Then we'll run into a contradiction. Okay, so what does it mean? Well, it must be the case that B must be 0. So if this statement is true, then it must be that B is 0. Why is that? Samarth, do you see why that is?
Just a second, sir. B is equal to B.
Yeah, so if it is the
Acha,
case
yes,
that this
sir.
combination disappears, yeah, go ahead.
Yes, sir. So because if B is not equal to 0, then it will be spanned by the following vectors, and that is it is given that thus S does not span B beta.
Exactly, right? So we basically assumed that beta does not belong to the span of S, right? But if B was not 0,
Yes,
right,
sir.
this equation would allow us to write beta as a linear combination of alphas, right? Which is what this object is doing.
Yes, sir.
Okay, and then this would imply that beta is in the subspace, right? It would imply that beta is in span of S, which we know is false, but that is a contradiction.
Yes, sir.
Okay, so it cannot be that beta
Yes,
is
sir.
non-zero. So then beta has to be 0. So now what is left of that equation? Now we have this equation left, right? That it's a linear combination of alphas, which is equal to 0. Now the point is that since S is linearly independent, okay, so first of all, is this clear? Right? We just said beta 0. We did nothing else.
Yes, sir. Yes, sir.
Okay, right? And now the claim is that since S is linearly independent, okay, so can this statement be true? What was your name again? Samarth. Yeah, can this statement be true, Samarth? Can you have a linear
No, sir, because
combination of linearly independent vectors sum to 0?
no, sir, because S is linearly independent, so we can't find such constants which are not
Exactly.
all 0 and this. Yeah.
Precisely. Okay, so the only way
Yes.
this can happen, because S is linearly independent, is if all the C's are 0. Okay, and so what do we have? We have the fact that the only way such a linear combination would give you 0 is if all the scalars are 0. But that is the definition of being linearly independent, right?
Yes, sir.
Okay, so okay, so it's actually not really a proof by contradiction. They're just going to, okay, so the goal here is to argue only holds, this only holds when CIs and B are all 0. Okay, so
Yes,
that's the proof. Okay, thank you so much. That was very helpful. Now let's maybe look at theorem 5. Is that okay? Do you want a minute or two? I guess for you at least it's okay. I'll just maybe wait for like a few seconds for anybody else who's trying to absorb the proof. And then
Yes.
I think I can end with the next theorem statement. All right. So let's continue then. So theorem 5 says the following. It says, if W is a subspace of a finite dimensional vector space V, okay, so W is a subspace of V, okay, then every linearly independent subset of W is finite and is part of a finite basis for W, okay. So then this implies any linearly independent subset, say Wi of W, is finite and part of a basis. Okay, so that is the theorem statement. I don't think we'll be able to do the proof right away. Yeah. Okay. So I think maybe it's a good time to stop. Maybe I will send you a recording of some of the.
Yes.
Yeah, at least maybe until before theorem 6 starts, I'll maybe send you a small recording so we don't fall behind. But that is
Sir,
roughly
what
the
would
idea.
be the syllabus for quiz?
So this will be communicated to you over Moodle. think the other classes are not exactly going at the same pace. So I think section 2.2 until section 2.2 roughly, but for the final confirmation, we'll send over Moodle by the end of the day. Is that okay?
Okay.
Okay, perfect. All right, you guys, it's time. I don't want to take more of your time. Thank you so much. And have a good afternoon. Goodbye. Thank you.